last class we were discussing the voltage transfer characteristics, right? Characteristics called VTC, the abbreviation. Okay, and just to remind you, this is my inverter that I constructed last time. We looked at various combinations of charging a capacitor and discharging a capacitor with Nmos, PMOS. We looked at all four combinations and then concluded that PMOS can be used only to charge a capacitor, Nmos can be used only to discharge a capacitor, so that the output voltage swing is actually rail to rail, and therefore our CMOS inverter, complementary metal oxide semiconductor inverter, is made of both Nmos and PMOS. Okay, there are alternate ways of making these inverters which you will see in the tutorial. For example, I can replace the PMOS with a resistor. Even then you will get an inverter, right? Voltage swing may not be rail to rail and all that, but you can analyze that as part of the tutorials based on what I am going to teach today. Okay, so V in and V out. Okay, and we said that intuitively we were able to arrive at this VTC, right? So if I sweep V in, right, and plot my V out, and I sweep V in from 0 to VDD, it goes through certain transition points. The first transition point happens to be at VTN, because until then the NMOS transistor is not turned on, and if the transistors are considered to be ideal, it means that there is zero leakage current, and therefore VTN is the first point. When V in crosses VTN, some non-zero current can flow through the NMOS transistor, right? And then we had another condition which is basically VDD plus VTP. Remember that, again let me keep reminding you, VTP is a negative number, whereas VTN is a positive number. Both of these invariably will be the same in magnitude, but it will be opposite in sign, plus 0.5 volt, minus 0.5 volt, right? So VDD plus VTP is actually less than VDD, okay, and this point is of course VDD, okay. So if I look at this thing here, output will start at VDD, perfectly at VDD, if the NMOS current is 0 before VTN, which is true if it's an ideal transistor and there's no leakage current. So it will be perfectly at VDD. And remember, what is our constraint? IDSN is equal to minus IDSP. This is the constraint. This is not an artificial constraint that we are imposing. It happens because the two transistors are in series, and therefore the series currents have to be the same, which means V out will adjust itself so that these two currents are always the same. At all, for all input combinations, this is true, right? And again, to remind you, this is the drain for the NMOS, this is the drain for the PMOS, source is fixed at VDD, okay. And we also evaluated VGSN equals V in, VDSN equal to V out, VGSP equals V in minus VDD, then VDSP, V out minus VDD. These were the 5 equations that we used, okay. So the voltage transfer characteristic starts off at VDD. Once you cross VTN, there is some non-zero current, so V out will now start dropping from VDD, right? Because some non-zero current has to flow through the NMOS transistor. That means there has to be some VDS across it, right? And VDS of the NMOS transistor is V naught. So the V out will sort of start dropping a little bit, right? For the PMOS, that is, I'm sorry, okay. This will drop like this, and again after VDD plus VTP, it will come back to 0. Output will be perfectly 0, okay. So if you look at the region of operation, we said Nmos is off, Pmos is in linear. Here Pmos is off, Nmos is in linear, right? Then we had one more region somewhere in between. It goes through, where in this region Nmos is going to be in saturation. So the moment Vin crosses Vtn, the Nmos turns on in saturation, Pmos will turn on in, of course Pmos continues to be in linear region. In this region, both N and P will be in saturation or velocity saturation, depends on whether it's a long channel or short channel device. This region is going to be, what is N and P? Yeah? No. Yeah, Nmos linear, Pmos saturation. So it's exactly a dual. Okay? So this is what we derived last class. The regions were 1, 2, 3, 4 and 5. Okay? So intuitively we came up with this picture. Okay? Now the question is, how do you actually arrive at these exact numbers? And that is what we are going to look at in this class. Okay? Especially when you are trying to do, for example, the PMOS is not, if the PMOS, instead of PMOS I put a resistor, then what do you do there? So in that case, we resort to something known as a load line analysis. Okay? Load line analysis is the following. I have the inverter like this. I have two devices each of which has its own current equation, right? And it has a constraint that is being imposed because of the way in which we have connected these devices, that the two currents have to be the same, right? So if you look at this, V in is here, V out and the currents are sort of in some sense constrained. It can't take any arbitrary values, right? If I tell you that my V in is so and so, then to satisfy both N and P constraints, V out will settle to some particular value appropriately, right? So what you do is, to analyze this, you free this constraint variable. So you make V naught as a free variable and then you sweep V naught from 0 to VDD and then you look at the currents for both N and P. As a free variable you do this and then you impose the constraint that these two currents have to be the same. Then you find out where these two meet. That will be your actual V naught that it will settle to. Okay, so we look at that particular example. Let me just write the 5 equations again. IDSN equals minus IDSP. Then we have VGSN equal to V in, VDSN equal to V out, VGSP equal to V in minus VDD, VDSP equal to V out minus VDD. Okay, so what I'm going to do is, I'm going to free this variable V naught. Okay, I'm going to basically make it like this. V in, this is VDD, then I have V naught here. Okay, I am going to have a current which is going to flow from drain to source like this, IDSP. Okay, V naught will be swept from 0 to VDD. Clear? I am also going to free my V naught for the NMOS transistor. V in is here, current will flow like this, IDSN, and this is my V naught. Okay, I am going to now free this variable, sweep it, find out what the currents are, and then I will equate these two in the end. and then find out what the V naught should be. Okay, clear? So in order to do this, I am going to now plot it for various values of V in. Okay, so it's very natural now that we looked at some 5 regions of operation, right? So I look at 5 different values of V in. Okay, point is sweep V naught with V in as a parameter. Okay, so I am going to consider V in equal to V1, V2, V3, V4 and V5. V1 will be less than VTN, right? The first region of operation. This I am going to say is V1 is less than VTN. This will be greater than VDD plus VTP. V3 is some value I am going to choose so that both transistors sort of operate in saturation region. Okay, so both saturation region. Okay, V2 and V4 will be chosen such that one is linear, other is saturation and vice versa. Okay, I just need to, actually I should do this for a continuum of VGS so that you can see what comes, but since we have only limited plots that we can do, I am choosing this very specifically. Clear? Okay, yeah. So now what I want to first do is to plot my Nmos current. Okay, Nmos ID versus V out, right? I will say IDS versus VDS actually. What is VDS for the Nmos? It is V out. So there is no big thing there. IDSN versus V out. I am going to sweep V out from 0 to VDD. Okay. What is the current through the Nmos transistor when V in equal to V1? As I told you, I mean V1 as defined here below VTN, 0. Okay. So now I will use some special colors so that we don't confuse things. So the current through this guy, irrespective of what your V out is, whatever the VDS is, current has to be 0 through this transistor. The transistor is not turned on. Okay, and here is my VDD. Fine. Now I take my V in slightly above VTN. So what will be the current through this and how will this plot look like? It's basically going to go through our earlier equation. So it will be something like this. Correct? This is for V in equal to V2. Now I am going to take V in equal to V3. Okay, which is obviously higher. So therefore this again will go somewhere here and it will look like this. Okay. For simplicity, let me assume that this is just V in equal to 0 volt. Actually it is from 0 to VTN, it is just the same thing. Okay. Then I am going to assume another color I need now. So let me take this. V in equal to V4. V4. And of course, when V in equal to VDD, I will have the highest possible current through my Nmos transistor. Okay, and therefore for that I will use maybe blue is over. Okay, V in equals V phi, right? Or I will just call this VDD because that is now V in equal to 0. Okay, yes. Yeah, it can get saturated. So let's not go into that detail for now. So let's assume that this is a long channel device. Okay, I've just shown non-zero channel length modulation for now, but let's assume that the velocity saturation doesn't occur here. Okay, yeah. Now I want to first plot IDSP versus VDSP for the PMOS transistor. I am not looking at V naught, nothing, for various values of V in. Okay, IDSP versus VDSP, which quadrant will it lie? This is the third quadrant, right? So therefore I need to look at the plot now in the third quadrant here. Okay, just one constraint we are going to introduce now, which is basically VGSP is V in minus, what is VGSP? V in minus VDD. Okay, so now for V in equal to 0, VGSP is how much? Minus VDD, right? So if I now sweep my VDSP from 0 to minus VDD, I will have the highest possible current through that transistor, right? So the key thing to note first is the corresponding blue curve here, which is the same current for V in equal to 0, is actually going to be the highest. This is for V in equal to 0. Okay. Now what happens when V in equal to V2? Slightly higher, the VGSP is now dropping, mod VGSP is dropping from VDD to slightly lower. So the curves will actually be an inverted version of that. Lowest current there corresponds to highest current here, because I am now looking at it for the same V in. I am not looking at this for VGSP. It is for the same V in, because now VGSP is V in minus VDD. That I have already incorporated. Okay. So therefore the curves, if I color code correctly, the magenta will basically come out like this. V in equal to V2. Then the green will come out like this, right? Then orange will come V4. Where will the curve for V in equal to VDD be? 0, right? Because now VGSP has gone, mod VGSP has gone below mod VTP, correct? So therefore this final curve is going to sit on this x-axis like this. Okay, now these are complete free variables. We have not imposed any of our constraints. We will now impose the first constraint, which is, I am going to say IDSN equals minus IDSP. What will this do? It will mirror it about the x-axis, right? So therefore the first curve will just remain as it is, and this is one. Then okay, and can manage this. Yeah, approximately, not greatly drawn, but fine. Okay. Now I want to superimpose this on my IDSN versus V out itself. Remember, now this curve is ID minus of IDSP versus VDSP. This axis, whatever curve we have drawn, is these curves here are all IDSP, minus of IDSP versus VDSP. But what is VDSP? This is nothing but V0 minus VDD, right? Therefore, if f of x is there, how does f of x minus x0 look like? Move to the right, correct? The whole thing just shifts. So x equal to 0 will happen at x equal to VDD, right? Because it is V out minus VDD. So now we are going to redraw these curves quite carefully, and I am going to make this transformation of going from here to here. I am going to make this minus IDSP versus V out minus VDD, right? Or rather, it's going to be with respect to V out. Yeah, correct. Sorry, this will be with respect to V out. You're right. Correct. Okay, so now all we have to do is make the plot wherever IDSNs and minus IDSP meet. That will be the operating point. Your V out will settle to that particular value finally. Okay, so let's go ahead and draw these curves. For V in equal to 0, how is the curve going to look? It's this curve, right? That's going to shift all the way there, correct? Oh, sorry. Oh, I can actually move it? Wow. I didn't know this. Brilliant. Okay. I would have mirrored that also then, right? Okay, anyway. What is the point of intersection? At VDD, right? The two curves, blue curves, meet only when the current is actually 0. The key thing that you have to notice is there are many points of intersection here which make absolutely no sense because they are for different V-ins. In a textbook, when you take it, especially Indian edition, because it's in black and white, you cannot make out this. So that's why it's important to color code this, or by the foreign edition, you will see the colors there. It sort of makes it easy for you. Okay, so now let me, yeah. Similarly, I am going to move this curve. What do I do? Right? So it's going to start from here. Yeah. So now where do these two curves meet? Yeah? Here, right? This is my point of intersection. Correct? Now let me ask you a question. In which region is the Nmos transistor? Which region is the PMOS transistor? Nmos is in, because if you just look at it, you will know the current is in saturation region, whereas the PMOS current is in linear region, right? So this point corresponds to Nmos being in saturation, PMOS being in linear region. Okay? Similarly, I can now move this guy. Oh, what is this? me just, maybe this alone I will just redraw it. For Vn equal to V3, obviously this is my point of intersection. Very evidently N and P are in saturation region, and again this I can sorry. Yeah, just to, yeah. So this point of intersection is here. What is the region of operation for N and P? Huh? Nmos is in linear, Pmos is in saturation, right? So this is N in linear, Pmos in saturation region. Okay, and of course now the final one is for the Vn equal to V5, which happens to be 0 along the x-axis. Point of intersection is origin. Okay, so this guy is again what? Nmos in cutoff, Pmos in what? Linear region. Is the previous one, yeah, Pmos, sorry, Pmos is cutoff. Yeah, Pmos is cutoff, Nmos in linear. Okay. Now from here it's also very easy to find out what the corresponding V out is, right? When Vin equal to 0, it has to be VDD. Okay, this guy here, V out is equal to VDD, exactly equal to VDD when there is no leakage current. And this guy is how much? Maybe I should use the same color. V out equal to VDD. Okay, this one is somewhat close to VDD, right? Less than VDD but close to VDD. So this is V out is approximately close to VDD. Maybe approximately but less than, I will just add that symbol. Okay, this is clearly, you can see V out is somewhere here, halfway, somewhere here, right? VDD by 2 approximately. V out. What about this? V out is approximately greater than 0 but very close to 0. Fine. And here of course V out is exactly 0. Okay. Now I can ask you the question, in which of these regions is the current going to be maximum? The third region, right? Basically that's where this particular, the green intersection is when the current is also maximum, because this is the maximum current that is allowed to flow when the input goes from 0 to VDD.